So let's look at to the strength of acid and base. Okay, we know that the acid can be strong acid, weak acid. Same goes with base. It can be weak base or strong base. So the acidity or the basicity strength is actually depending on the extent of the dissociation of the acid and base in a reaction. Okay, so if we say that, or if we categorize an acid or base as a strong one, it means that they are the substance that completely ionize in water. They are 100% dissociate into ion. Okay, however, for the weak acid and weak base, they are the substance that partially dissociate in water. So this description of the strong acid, strong base, weak acid, weak base, as you have to be able to differentiate them and identify each. So strong acid include hydrohalic acid, HCl, HBr, HI, and then the strong acid can be oxo acid that contain oxygen atoms exceed the number of the ionizable proton. Okay, by 2 or more. For example, we have a nitric acid, H2SO4, HClO4. Okay, as for the weak acid, okay, it is include HF, the only hydrohalic that is weak. Okay, and then the acid in which H is not bonded to the oxygen or to the halogen, for example, HCN. Then weak acid can be oxo acid in which the number of oxygen equal or exceed the number of the ionizable protons by 1, for example, HClO, HNO2. And all the carboxylic acid with the general formula of the RCOOH, for example, CH3COOH, C6H5COOH, they are all weak acids. So it is easy for us to identify. As long as we found COOH, we know that they are weak acid. Other than that, okay, no choice, we have to memorize it. Then the category of the base, the strong base include the water-soluble compound that contain O2 minus or hydroxide ion. Okay, and the cation that usually those of the most active metal. Okay, the base that is formed by active metal, lithium, sodium, potassium, rubidium, cesium, and contain OH in their formula. As for the weak base, ammonia, amine with the general formula with the lone electron pair. Okay, if we have this example, we have HA. For example, we have 100 molecule of HA. Okay, when HA undergo dissociation, it will produce 100 ion of the H3O plus and 100 ion of the A minus. No more HA left after the dissociation. So that is the strong acid example. If let's say we have 100 molecules of the HCl, and we know that HCl is a strong acid, after HCl undergo dissociation, okay, we have no more HCl, we have H plus, Cl minus, and H2O. Okay, because HCl will be dissociated when it is dissolved in water. However, if you have a weak acid or weak base, for example, if we have 100 molecule of HA acid, after dissociation, we have a small amount of the H3O plus and A minus that is produced, and major of the HA remain as HA. It's slightly ionized into ion or partially ionized into ion. Okay, if we say we have HA undergo dissociation in water, we have example here acetic acid CH3COOH. Okay, after the dissociation occur, after the equilibrium achieved, we have H3O plus, we have CH3COO minus, and we still have CH3COOH remain in our reaction vessel. That's the difference between weak acid and strong acid. Same thing that is happened for strong base and weak base. So let's recap. The strong acid dissociate completely into ions in water. Okay, while the weak acid dissociate very slightly into ions in water, slightly or partially dissociated. Makes the Kc, remember the Kc, the equilibrium constant, less than 1. Okay, so let's look at to the acid dissociation constant. So we have this reaction Ha plus H2O produce H3O plus A minus. Look at to this reversible arrow means that okay, this is the reversible reaction. Okay, it can occur in a forward and also reverse direction. Okay, when we write the Kc expression of this reaction, it will be Kc equal to H3O plus, concentration of the H3O plus, multiply with the concentration of the A minus over concentration of the Ha. Okay, no H2O come out in our Kc expression because H2O is liquid. Okay, so that is the Kc, or to be specific, this is the acid dissociation constant, or we call it as the Ka. So if we have a stronger acid, the concentration of the H3O plus that is produced during the dissociation will be higher. It will make the Ka value become greater. However, if we have a weaker acid, okay, we will have a lower concentration of the H3O plus that is produced during the dissociation. Then we will have a smaller Ka value. So remember, the Ka value only present for a weak acid. Okay, because for the strong acid and strong base, okay, they are completely ionized. So the arrow is only forward arrow. This reaction is only occur in a forward direction. So we will have no Ka expression or Kc expression for this strong acid and strong base dissociation. So Ka and Kb. So for Kb, it is for base. Okay, only present if we have a weak acid and weak base because they are reversible reaction. Okay, so in this table, we have a list of the weak acid: chlorous, nitrous, HF, formic, acetic, propanoic, until hydrocyanic acid. Okay, so they are all weak acid. Okay, how do we know that they are weak acid? Because they have its acid dissociation constant, its Ka value. Okay, and then among weak acid, there will be one that is stronger than the others. There will be one that is weaker than the others. So when we look at to this Ka value, we know how strong they are, okay, or how much H3O plus that they can dissociate. And if it has a greater Ka value, for example, chlorous, it is 10 power of -2. Of course, that it is stronger than nitrous, which is 10 power of -4. And the weakest one among these acids is hydrocyanic acid because it has the smallest Ka value. Remember, okay, Ka is actually derived from the Kc expression, but since that this reaction specifically is the acid dissociation process, then we don't call it as a Kc. Okay, it is a Ka, and it stands for the acid dissociation constant. We refresh back the Bronsted-Lowry base. It is defined as the species that accept proton or H plus. So we know that the base categorized into strong base and weak base. So if we have a strong base, they dissociate completely into ion. Can be represented by example of the sodium hydroxide. It is one of the strong base. Okay, we have a sodium hydroxide aqueous. dissociate into Na plus aqueous and OH minus aqueous. Okay, so look at to this arrow. This is a forward arrow, means that it is not a reversible reaction. The same as strong acid just now. Okay, when during the dissociation, it is not a reversible reaction. They cannot reverse back into its sodium hydroxide. As for the weak base, when they dissolve in water, they are partially ionized, so that the equation will have a reversible arrow here. For example, if you have a base B aqueous react with the H2O liquid, it will turn to the BH plus and OH minus. Okay, so since that base is a species that accept H plus, according to the Bronsted-Lowry, that is why B receive H plus from H2O and become BH plus, and then H2O turns to OH minus. So the base dissociation constant, or if we try to express the equilibrium constant for this dissociation of base B, the equation will be Kc equal to BH plus concentration multiplied with the OH minus concentration over B concentration. No H2O come out in our Kc expression. And then since that this Kc expression of this reaction is specifically for the base dissociation process, then we don't write it as Kc, but we write it as the Kb, or base dissociation constant, is equal to this multiplied with this over this. Okay, so Kb is the base dissociation constant. Just now Ka is the acid dissociation constant. Okay, so the value of the Ka and Kb will identify whether a base is the strong base or it is a weak base. Okay, among the weak base, which one is weaker and which one is stronger? So if we have a stronger base, okay, it will dissociate more hydroxide ion, okay, during the process, so that the concentration of the hydroxide will be higher and it will lead to the greater Kb value, because hydroxide is the numerator. So when the numerator is greater, it will make the Kb become higher. As for the weaker base, it will dissociate less hydroxide ion, makes the concentration of the hydroxide lower. Then when we calculate the Kb, since that the OH is lower, when we calculate the Kb, then we'll get a lower Kb value or smaller Kb value. So we have to remember that actually no base dissociate in a solution, but the ions are produced when the base react with the H2O aqueous, except for the strong one. So in this table, we have a list of several weak base. The higher the Kb value, the stronger the base. Means that during the dissociation or reaction of the base in water, they liberate more hydroxide as compared to the one that have a lower Kb value. For example, in this case, aniline is the weakest one because it has the lowest Kb value, shows that aniline produces the least amount of the hydroxide during the reaction with water.